Hi, our today's topic is multivariate random variables and joint distributions. Until now, we discussed only scalar random variables. So this was a situation when we observe just one single number as a result of our repeatable experiment. So every time the experiment is done, every time we know the outcome of the experiment, we have just one single number. For example, I choose a random person, and this number may be his or her weight or height or age or salary or something else. Now, let's imagine a situation when we observe not one, but two numbers. So I'm interested not only in a weight of the person I have chosen, but in their weight and height. So I observe a pair of numbers each time the experiment is done, each time the experiment is repeated. So I can say that this pair of numbers, these are two random variables. And if these two variables are related to each other somehow, it is not enough to know the distribution to know just their own distributions. So if these are two random variables x and y, it is not enough to know distribution of x and the distribution of y to solve problems on these two variables. We are to know what is called joint distribution of these two random variables. So let's start with the most simple case, with the situation when these two variables are both discrete ones. So x and y are two discrete random variables. X can take several values, so x has several possible values, x1, x2, and so on, up to xm, and y also has several possible values, y1, y2, etc. to yn. And so joint distribution of these two random variables can be described with a table you see now, and for each pair of values xi, yj, for each pair, this table gives us a probability, so gives us the probability that this pair of values will be observed in our experiment. So each time the experiment is done, we get not one number, but we get pair of numbers, value of x and value of y. And for each possible pair of values, this table gives us a probability. So Pij is a probability that x takes value xi and y takes value yj. What are these probabilities with dots in indexes that you can see in the last column and last row of this table? So these are sums of probabilities. So p dot 1 is p11 plus p21 plus pm1. So you add all probabilities that are in the first column and you get this p dot 1. So p dot 2 is a sum of all probabilities that are in the second column and so on. So, and p1 dot is a sum of probabilities from the first row, p2 dot is a sum of probabilities from the second row, and so on. So these are sums of probabilities. What is the physical sense of these sums, physical meaning? So when you summarize, when you add, let's say, all probabilities that are in the first row, what do you get as a result? So these are probabilities that x is x1 and y is y1, that x is x1 and y is y2, that x is x1 and y is y3, and so on. So these are all probabilities that x is x1, and they differ only in value of y. So these are probabilities for the same value of x and different possible values of y. And when we add them, so we get the probability that x is x1 and y will take any of its possible values. So in other words, this is probability that x is x1 and no matter what the y is, what value y takes. So as you can see, as you can understand already, these sums are just probabilities that we usually see in distribution tables of scalar random variables. So pi dot is a probability that x will take value xi. P dot j is probability that y will take value yj. And so when we know these probabilities, when we know these sums, we can fill the distribution tables of x and y respectively. So these are, in other words, these are PMFs, probability mass functions of x and y respectively. So using these probabilities with dots, we can fill these distribution tables. And these distributions are called marginal distributions of x and y. So this is just a matter of terminology. If we are dealing with a joint distribution of two discrete random variables, not only discrete. So if we deal with joint distribution of two random variables, if we find own distributions of x and y, we call them marginal distributions. Now, what about continuous distributions? So let's consider a situation when both x and y are continuous random variables. As you know, if we have a scalar continuous random variable, the natural way to describe its distribution, to define its distribution, is to use PDF, probability density function. So if we have a pair of continuous random variables, we can also define a joint PDF, joint probability density function of this pair of random variables. So as pair of random variables, so its value is a pair of numbers. That is why this is a function of two arguments. So it is defined as a function of x and y. So its definition set is a plane, xy plane. And we can imagine that the graph of this function is something like what you see here. And as in scalar case, when you want to find probability that your random variable of your interest will take value from a given interval, you integrate its PDF over this interval. And here, so in two-dimensional case, you also, to find a probability that your two-dimensional random variable, your pair of numbers, will take value from a set on the xy plane, you are to integrate their joint PDF over this set. So probability that you will get pair of numbers x, y that belongs to some set G is double integral over G of joint PDF, of the joint PDF of x of f of xy. So, and this equation, this formula can be assumed as a definition of what joint PDF is. So, joint PDF of two continuous random variables is such a function that for every set, for every two-dimensional set, probability that pair of numbers x, y will belong to this set can be found as a double integral over this set of this function. So such a function is called joint PDF of x and y. As for marginal distributions in continuous case, it is a little bit more difficult thing to find them. So more difficult than in discrete case, but still here are the formulas that show us how to find PDFs, marginal PDFs. So PDFs of x and y when you have joint PDF. So you are to integrate the joint PDF to integrate it over y if you need marginal PDF of x, and to integrate it over x if you need marginal PDF of y. So if it is possible, if this function allows integration, so if integral can be found in elementary functions, so this problem can be solved. So, as you know, for scalar random variables, the common way, third way, to describe its distribution, to define its distribution that is common for discrete and continuous random variables is cumulative distribution function. And in two-dimensional case, we also can define a joint CDF, joint cumulative distribution function of two random variables. And joint CDF exists both for continuous and discrete random variables, and its definition is very similar to what we have in scalar case. So joint value of joint CDF so is probability that x is less or equal than small x and y is less or equal than small y. So this is joint probability. So this is probability that both events will occur. So x is less or equal than small x, and not or, but and y is less or equal than small y. So in other words, geometric sense of this is that this is probability that our two-dimensional random variable will take some value from this quarter of the coordinate plane, so that it will take a value that this point will be somewhere left of x and somewhere down of y. So in this quarter of our plane. As you know, scalar CDF has some important properties that limit its possible values and describe its behavior. And so the same situation we have for joint CDF. If we substitute minus infinity for either for x or for y, the result is the same. Value of joint CDF will be 0. So as what is it? So when we substitute minus infinity, this is probability that x or y will take value less or equal than minus infinity. That is impossible. And no matter what the value of the other variable is, as one of two events is an impossible event, so then intersection of an impossible event with any other is also an impossible event, and so probability is 0. Then, if we substitute plus infinities for both x and y, we'll get 1, because with probability 1, x and y will take some values that are less or equal than plus infinity. Then, if we substitute plus infinity for either x or y, we will get marginal CDFs. So marginal CDF of x is joint CDF of x plus infinity. Marginal CDF of y is joint CDF of plus infinity y. So when we substitute plus infinity for x, for example, that means that we agree for any value of x. So any value of x is acceptable. So it means that we are interested in probability that y is less or equal than little y, and x can take any value. Any less or equal than plus infinity. That means simply any value. So the same is for the marginal PDF of y. So when we for the marginal PDF of x, if we substitute plus infinity for y, that means that y can take any values, and we are interested only in x values, so we get PDF of x. So there are also important formulas that show us relationship between the CDF and the PDF. As you know, in scalar case, PDF is a derivative of the CDF, and the CDF is an integral of the PDF. So the same situation is here, but a little bit more complicated, as now we deal with the functions of two arguments. And so that is why joint PDF is second mixed partial derivative of the CDF. So the CDF is differentiated over x and then over y, or vice versa. And joint CDF is a double integral of the joint PDF. And this double integral is also calculated over x and over y. So that is how you can find the PDF if you have got the CDF, and vice versa. And as for discrete case, usually we don't deal with joint CDFs in discrete case. So yes, a joint CDF can be defined for a pair of discrete random variables also. So this definition you see now, it is valid both for continuous and for discrete random variables. But in discrete case, it is usually enough to have this table of joint distribution, and usually we don't need the CDF. Actually, the shape of the CDF in this case is too complicated to deal with it. So. Now, let's discuss an important feature of random variables, their independence. So a pair of random variables, so two random variables x and y, are called statistically independent or simply independent if their joint CDF is equal to the product of their marginal CDFs. So I will tell you about this in details a little bit later, but you should know that this type of dependence or independence is usually called statistical independence. So it's better to say that two random variables are not just independent, but statistically independent. But in real life, this word statistically is usually dropped. And they usually say independent random variables, independence of two random variables, and so on. So, and please mind this situation that when a statistician says independent random variables, he means statistically independent. So he means independence in terms of this definition. So if two random variables are dependent, that means that this equality you see in this definition is not true. So if the joint CDF is equal to the product of marginal CDFs, they are independent. If the joint CDF is not equal to the product of the marginal CDFs, they are not independent, or they are statistically dependent, we can say. So this definition is usually not so very, how to say, applicable. So sometimes it's difficult to apply it to check if a pair of random variables is dependent or independent. So there are two consequences of this definition for discrete and continuous random variables respectively. So that are much more, how to say, convenient to use. So for discrete random variables, there is a theorem that they are independent if and only if joint probability is equal to the product of marginal probabilities. So if for any pair of values small x and small y, probability that both x is equal to small x and y is equal to small y is to be equal to the product of probabilities that x is x and y is y. So if it is true for any possible pair of values, then x and y are independent, and vice versa. As for continuous random variables, so they are independent if and only if the similar equality as we see in definition of independence is true, but not for the CDFs, but for PDFs. So we can sometimes even these two theorems you see now, they're used as definitions of independence. So independence is defined separately for discrete case and for continuous case via probabilities and the PDFs respectively, with avoiding using this common definition with CDFs. So in different textbooks you can find different definitions. So these two equalities you can see in these two theorems are usually used in practice to check if a pair of random variables is independent or not. So another important numerical feature that we usually find when we're dealing with a pair of random variables are covariance and correlation. Covariance of two random variables is defined so as follows. So this is expected value of x minus ex times y minus ey. And a correlation or correlation coefficient is defined as covariance divided by the square root of the product of variances. So there are different notations used for covariance and correlation. Sometimes they prefer these symbols like cov and cor. Sometimes letter K is used for covariance, sometimes letter C, the first letter of this word, covariance. And for correlation, Greek letter rho and Latin letter R are also frequently used. So to describe this coefficient. Terms correlation and correlation coefficient are to some degree synonyms, but be careful, please, because in some textbooks they prefer to call this numerical coefficient, to call it correlation, and a type of dependence between two random variables is called correlation dependence or correlative dependence. And in some books, they usually use this term correlation for the type of dependence, and for the numerical coefficient, and the numerical coefficient is called correlation coefficient. So the word correlation can be used either for the coefficient or for the type of dependence. So if it is used as a description of the type of dependence, then coefficient is called correlation coefficient. So if it is used for the coefficient, then type of dependence is called correlation dependence or correlative dependence. How about the physical sense, physical meaning of what correlation is? We will discuss this a little bit later. Now the first step is to understand mathematical definitions. And another term that is often used, uncorrelated random variables. So two random variables are called uncorrelated if their covariance and the correlation are both equal to 0. So as you can see from definitions, if covariance is 0, automatically correlation is also 0, and vice versa. As correlation is covariance divided by something, so that is why they are either both equal to 0 or both not equal to 0. So that is why covariance equal to 0 or correlation equal to 0 is enough to call these two random variables uncorrelated. So if this equality is not true, so if covariance and correlation are not equal to 0, so they are called correlated. So, and these are main properties of covariance and correlation. So covariance of x and y is equal to covariance of y and x. So it can be easily seen just from the definition. We see that this is an expected value of x minus ex times y minus ey. So as we can change x and y, and the result will be the same, that is why covariance of x and y is equal to covariance of y and x. Then covariance of x and x is equal to the variance of x. So if you substitute x for y to the definition of covariance, you'll get the definition of variance. Then covariance of linear combinations, of linear functions of x and y. So of ax plus b and cy plus d is equal to ac times covariance of x and y. So these b and d, non-random numbers added to our random variables, do not affect the covariance. Only coefficients, non-random coefficients, affect the covariance. Then a formula for the variance of a sum of two random variables. As you remember, I told you that variance of a sum is not always equal to the sum of variances. So there was a property of variance such that variance of x plus y is not equal to variance of x plus variance of y, at least in general. So this is the formula. Number 4 is the formula for the variance of a sum of two random variables. This is sum of variance plus 2 times their covariance, plus double covariance. So as you can see, variance of a sum can be equal to the sum of variances, but only if covariance is 0. So only for uncorrelated random variables, variance of a sum is equal to the sum of variances. For correlated, this is not true. Then number 5 is the formula we usually use in practice to find covariance. We usually use not the formula we see in the definition of covariance, but we use this formula. It can be just derived by using simple properties of the expected value. So covariance of x and y is expected value of x times y minus expected value of x times expected value of y. So as it is usually much more easy to find e of x, e of y, and e of their product than to deal with the formula we see, with the expression we see in definition of covariance. As for correlation, the first important thing is that correlation of any random variable with itself is 1. The second, correlation can take values from -1 to 1. So it is a normed coefficient. So covariance can take any values from -infinity to +infinity, and correlation can only be from -1 to 1. And if it is equal to 1, this means that there is a functional linear dependence between x and y. So if correlation of x and y is equal to 1, this means that y is equal to ax plus b, where a and b are non-random coefficients, and a is positive. If correlation is -1, this means that y is equal to ax plus b and a is negative. So situation of correlation equal to 1 or to -1 means that there is a linear functional dependence, not statistical but functional, between x and y. So that means that if you know x, then you can you can calculate just the value of y using this formula, y equal to ax plus b. So later we will discuss also geometric meaning of correlation. And so also there is an important relationship between correlation and independence. There is a theorem that if two random variables are independent, then they are uncorrelated. So if they are independent, then their covariance and correlation are equal to 0. So if x and y are uncorrelated, they may be dependent or independent, so both are possible. But the one important exception is normal distribution. So this exception are normally distributed random variables. So if x and y both follow normal distribution, then they are independent if and only if they are uncorrelated. So in general, uncorrelation is just a consequence of independence, but not vice versa. But for normally distributed random variables, so independence and uncorrelation is actually the same. So if they are independent, then they are uncorrelated, and vice versa. If they are uncorrelated, they are independent. Sometimes we deal not with a pair of random variables, but with a number, with a set of n random variables. And in such situations, we usually say that we have a random vector. So random vector of dimension n that consists of n random variables x1, x2, xn. And in this situation, we can define covariance for each pair of elements of this random vector. So covariance of x1 and x1, x1 and x2, x1 and x3, and so on. And so then we can collect these covariances into a matrix that is called a covariance matrix. So this is a matrix that consists of covariances of all pairs of elements of a given of the given random vector. As you can see, diagonal elements of this matrix are variances, as covariance of any random variable with itself is equal to its variance. And this matrix is a symmetric matrix, as covariance of x1 and x2 is equal to covariance of x2 and x1. So that is why so elements above the main diagonal of this matrix and under it are equal. In a similar way, we can also define a correlation matrix. So this is the matrix that consists of correlations of the elements of a random vector. And so diagonal elements of this matrix are ones, as correlation of any random variable with itself is equal to 1. So in our course, we won't deal with random vectors of big dimensions, more than 2, but still you should know that there is such a feature of a random vector that is called covariance matrix, because in many problems of data science, of machine learning, they use covariance matrices of some multidimensional observations.